So we are coming close to the end of this chapter on ocean-atmosphere interactions. Let's just look at a few aspects of the coupled ocean-atmosphere models to close out. I already showed the observed rainfall estimates from satellites, coupled model simulations of the same thing showing clear problems in terms of rainfall intensity. Of course, you can look at duration, frequency, intensity, and so on, and there are some biases in all of them, but that's not the main point. The main point is to remember that just given the forcing at the top of the atmosphere, these coupled models are able to produce all these features. Although there is a little problem, they are all very reliable for many problems we want to deal with, including weather forecasts and seasonal to interannual forecasts, climate projections, and so on. And we looked at sea surface temperature biases as well. Remembering that climate model history has evolved over several decades and continues to be continues to grow to become more sophisticated Earth system models, including chemistry, human activities, and greenhouse gas changes, of course, and so on. I'm not going to go through this again, but we talked about the 60s and 70s atmospheric and land surface models, ocean models, their coupling, atmospheric chemistry models, their coupling, sea ice models, their coupling, sulfate aerosols, biogeochemical cycles, carbon cycle, marine ecosystems, ice sheets, upper atmosphere, dust, sea spray, carbon aerosols, interactive vegetation, dynamic vegetation models, and so on. So they continue to improve in realism, representation, resolutions, and so on, but yet we still have to do parameterizations of many things, including incoming solar radiation. So these are the 20 things that have to be parameterized. The list is from Comet program. I won't read all of them, but you know many of them: scattering by aerosols and molecules, vegetation, soil properties, rainfall, surface roughness, deep convection, emission of long-wave radiation from clouds, and so on and so forth. There are some major issues like cloud modeling and so on, but again, we are making great progress in terms of cloud resolving models, explicit convection models, and so on, and land ice models, and so on and so forth. So the scheme of the coupling of atmosphere and ocean model components is shown here, with the atmospheric general circulation model at this end, ocean general circulation model with sea ice models at this end. So there is information exchange through the coupler. I used this word coupler before. So the ocean is giving interpolated time averaged fluxes, and they come through sea surface temperature, sea surface salinity, and sea ice distributions, which affect the atmospheric general circulation model, which then gives wind stress, freshwater flux, and net heat flux, which then the model, ocean model grid and atmospheric model grids are not necessarily always the same in terms of longitude, latitude grids, but also ocean has boundaries, so you have to interpolate at the edges to make sure that you are not interpreting ocean points as land points or land points as ocean points, and so on and so forth. So there are many details involved. So you have this kind of interaction, and the integration time step may not also be necessarily the same, and how often the ocean gives the information to the atmosphere and how often the atmosphere forces the ocean, and all are kind of optimal choices. For example, atmosphere must consider diurnal time scale because it's very important, whereas the ocean may be running at daily mean, assuming that the diurnal cycle in the ocean are not so important. And it is done in a kind of two-step where you produce ocean SSTs and sea surface salinity, sea ice distributions, which affect the atmosphere, and when the atmosphere is being integrated, those are held constant. So for however long the atmosphere is integrating, the ocean quantities remain constant, and then ocean is forced again to produce these quantities, and then again ocean is held constant as the atmosphere is integrated. So all these kind of details we are not going to worry about, but there are some things we have to think about. It's called climate drift, for example. So I'm going to add a little bit to this discussion. I mentioned the coupler and the process, but I didn't point out this part here that's called flux correction. This was a method that was used early on, introduced by our Nobel laureate Tsuki Manabe, when initially couplings were done in the 1960s and 70s. Remember, the computers were not as powerful, though the models were run at fairly low resolution, and they were older generations of models which were not as detailed as the present ones. They didn't have as much data to parameterize or improve parameterizations, tune models, and so on and so forth. So the imbalance of energy in the models in a coupled integration were fairly large, which would become unrealistic upon integrating on anthropogenic timescales by increasing CO2 and so on. So Tsuki Manabe decided that correcting for the errors in the fluxes at the interface of the ocean and atmosphere was okay to get realistic coupled state, so that perturbations on those state due to things like greenhouse gas increases was a reasonable way to do things. Models don't do this anymore, but it's worth understanding that in the context of what happens in terms of a climate drift that require such flux corrections. So this is a work done by Tom Stoker himself here in 1992, using a ocean model coupled to a simpler atmosphere model as an energy balance model. So it's called the Bern 2.5D model. So it's not fully coupled in the sense the atmosphere is not represented with a full atmospheric general circulation model. So the ocean model is integrated to equilibrium by forcing with the restoring boundary condition that we talked about before. So you can see that the Pacific salinity, the Atlantic salinity, and the energy balance and top of the atmosphere imbalance is shown here, and the coupling of the equilibrated ocean to the simple energy balance atmosphere model is started at year 4000, which creates a quick kick to the system. So the energy balance is perturbed, energy imbalance is perturbed, and the Pacific salinity begins to increase because of the imbalance in the freshwater fluxes. Atlantic salinity begins to change as well, creating an imbalance at the top of the atmosphere, and this is caused in this model because of change in the meridional overturning circulation, or the change in meridional overturning circulation is created by the change in the energy balance, freshwater flux balance, salinity balance, and so on. So you can see that the meridional stream function in Sverdrups, 10 to the 6 cubic meters per second for max and min for the Atlantic and the Pacific are shown here. So there is obviously an impact of the salinity drift on the Atlantic and Pacific stream functions. So you can think of it as zonal mean meridional circulations in the two oceans. So this is still a problem in the current crop of models. So this is from CMIP 5 models, I think, or CMIP 3, it doesn't matter. So it is showing the way the models are run. So you take the coupled model, you set the CO2 levels to the pre-industrial level, let's say 280 ppm, and you integrate the coupled model for a long time. It's called free run, so that the coupled system comes into equilibrium. Equilibrium here just means that you have reduced the top of the atmosphere energy balance to as small as it gets in a given model. It will never get to zero. So in the control simulation, fixed 1870 greenhouse gas concentrations and some kind of initialization with observations is done, and then you reach that equilibrium state. You call it 1850, and then you begin to give it the observed increases in greenhouse gases, solar activity, volcanic forcing, aerosols, and so on. And you can see that the raw 20th century simulation is here. Historical greenhouse gas and aerosol concentrations are initialized from the control run at this point, and then the drift corrected, and then there is the SRES simulation, which was the CIMIP 3 simulation, where they were called special reports on emission scenarios and so on. So that's the future projection, but the model actually has a drift, and that's the drift signal. So if you don't do anything, you go here, but if you do a drift correction, then you see that your projected warming here is different than without correcting for the drift. So the equilibrium in control simulations reached after long integration. So you can see that the drift begins to flatten out somewhere here. So there is a drift in the sense of a remaining energy imbalance on top of the imposed greenhouse gas forcing and so on. So I don't want to say too much other than that to say that given the top of the atmosphere radiation forcing, the models take that energy, produce internal variability, internal circulation, ocean, atmosphere, land, and ITCZ, El Nino, monsoon, everything, but at some time scale the top of the atmosphere radiation balance should equilibrate, but the models continue to have a slight imbalance because of the model biases, which leads to global mean temperature drifting. Drifting means it just keeps going in one direction, as we saw here. This shouldn't happen. It should flatten out. So it flattens out after a long integration. In the meantime, you don't have time to resources to keep integrating to equilibrium. A coupled model is very expensive to integrate for a long time. So you use forcing on top of that drift that is still not equilibrated, and you do projections, but there are ways in which you can go and correct the simulation and the projection with the known drift in the model. So maybe I should leave it here and do the flux correction in the next podcast as the last podcast. Okay, again, hopefully this podcast is continuous and there is no jump because I stopped it and restarted it. I'll listen and make sure, but just make sure you get the points about coupled modeling. What are the issues with the forced ocean model or a forced atmosphere model, and then what are the issues in the coupled model just in terms of AC interactions and exchanges of information, and how the flux that the ocean sees and the flux that and the quantities that the atmosphere sees in terms of sea surface temperatures and so on can have biases with respect to observations. And there are many strategies used to correct those errors, which is called flux correction, and we will see in the next podcast how that flux correction was formulated, remembering that now it is considered a sin to do any sort of flux correction, even though Suki Manabe thinks that the kind of biases that persist in the models, like that double ITCZ, cold SST biases in the Eastern Pacific, reversed SST gradient in the Atlantic, reversed thermocline gradient in the Indian Ocean, and so on, can only be corrected with flux corrections. Well, he's an experienced man, a Nobel laureate, but the community is still not using any flux correction as of yet. But you can be sure that somebody is going to try it and see if that improves the future projections, and we'll wait for those results. Okay.